human cell has about 20,000 different proteins. It's like a city and you let everybody run sort of randomly, and still there are interactions somehow between all these components that creates at a higher level order and purpose. And I have a deep feeling that underneath all this mess, there must be ways in which also cells tame the complexity. And these are the rules that I would like to find. So to have control over the complexity of biological systems. What we're looking at here is the chemistry of a cell. And this is how you turn nutrients into the building blocks that cells need to do their job, basically. And this is where, you can think of finding the right targets for drugs. That's like the traffic outside, right? So the cars running through. Now, chemical reactions do not occur very spontaneously in cells. So we need a catalyst. And that catalyst is an enzyme. And an enzyme is a protein. And now what makes it really complicated is that, of course, this protein is the catalyst, right? But it is also possible that B affects the degradation of the protein. Or it affects directly the activity of the enzyme. And so there is multiple layers of feedback, and therefore we need regulation that make a unique cell, a liver cell or a blood cell, and it also makes a cell healthy or not healthy. And that also then gives you the clues on where you may want to interfere in case you want to turn a sick cell into a healthy cell. So just imagine this is just one enzyme that is synthesized and all these regulations on top of that, and we have thousands of those enzymes in the whole network and in just one cell. And then we have many, many, many cells. I try to deal with the whole map, and I make actually computer models of the whole map, trying to understand where the vulnerabilities are. So the big question, of course, is okay, you have this network and something is wrong in the disease. Where do you intervene? Right? That's the big question. Because now we have these blockbuster drugs that everybody takes, and we know that there's very often non-responders. So there's an enormous failure rate now. And there's also where the animals come in. The translation from animals to humans is just not very good. Let alone that a lot of experiments you cannot do on real humans. So what we make is computer replicas of these networks. The biggest one we now have has 16,000 reactions in it. And we can add a drug in the computer, let's say, and then run scenarios. So it's scenario testing, get a feeling for what works, what does not work. And in that sense, we've seen projects where we actually prevented a company from doing a lot of experiments that were very likely not being successful. Sort of my dream in the end would be if we can understand the rules to get to digital twins, as we call them, or computer replicas that allow us to really design drugs or design bacteria to do things that we want to do. That is going to be the future. Given all the complexity and all the uncertainty and everything we discussed, if you start to really think about this, and the more you know about this, the more unbelievable it becomes that a cell can do that. And they have sort of perfect design. They've dealt with all this uncertainty and all the noise that you have in a cell. So I have deep respect for cells.